All right, everyone, welcome back. So this week, today by midnight, you'll have to turn in experiment 11's post lab, and you have to have submitted your response for the lab activity. If you don't submit a response by midnight today, I will not grade the lab report. So just make sure you do that. Because doing the lab activity ensures you have the knowledge to do the post lab more effectively. Okay, so if you don't do the activity, you're going to lose the experience of actually seeing how the lab is done and concepts we cover. Okay, are there any general questions before I begin? Any general questions? Anything about the lab, lecture, grading? So the first experiments post lab on Gradescope has been released. So check out your scores. If you think I made an error in grading, you can request a regrade until the end of this class, until the end of the course. So you have until like March 12th, I believe, to submit a regrade. So I would, if you think you lost points, there's no hurting in submitting a regrade request. With that out of the way, let's go over this week's experiment. Sorry. Okay. So this week we are doing experiment 2, reaction of maleic anhydride to fumaric acid. So this is going to introduce some concepts about these two acids, how they're related, or maleic acid and fumaric acid, how they're related, and how we can use melting point to kind of determine the purity of our product that we get at the end. Okay, so our reaction for today, we're going to take maleic anhydride and I'm going to hydrolyze it with heat to maleic acid. So anhydride is essentially a carboxylic acid that lost its water molecule and it formed a new bond to oxygen. So you can see here, essentially, we took one of the carboxylic acids and we kind of closed the ring together to form this anhydride. So you'll learn about anhydrides when Dr. Levins talks about carboxylic acids, and when she goes into more like bio molecules such as sugars, and then amino acids and proteins, stuff like that. But this comes from a dicarboxylic acid, so a carboxylic acid that has 2 acidic groups at the end. And when we dehydrate, remove water from this molecule, we'll get maleic anhydride. But in this case, we want the acid, so we're going to take the anhydride, hydrolyze it with water, break it up in the ring, and form the maleic acid. Okay. So the next thing we would do is we're going to isomerize the maleic acid into its trans isomer, the fumaric acid. So remember that usually with a double bond, we can't rotate around it without heat. And in this case, that's what we're doing. But to help that process speed it up a bit, we're going to use an acid catalyst here to help speed up the reaction. Okay. All right. So I have a question for you guys, or for everyone, sorry. How do the cis and trans configuration differ? So how do they differ? So you'll need to kind of think about how do they differ and what kind of isomers they are. Okay, so think about like what kind of isomers these 2 molecules are, and how would you classify them? So just think about like the double bond. How do they differ in terms of the double bond? Okay. That's right. If you do not want to chat or answer the questions, it's fine. I'm just going to answer, and I'm going to pause for like a brief moment in case someone does want to answer. But if people don't answer for a while, I will just go ahead and move on. It's just to make the learning experience more interactive. because some people do learn better that way, such as myself when I was a student nearly 10 years ago. Okay, order of reagents. So the first thing we're going to do is convert maleic anhydride to maleic acid. So let's think about the order of reagents. So why do we boil the water before the maleic anhydride is added? Does anyone have any ideas? Any ideas why we boil the water before the maleic anhydride is added? Any ideas? Okay, so we're going to boil the water because we need to melt it first. So if we just add maleic anhydride into water, it'll react, but I don't think it will melt, and it might not dissolve as readily. So to make sure we get a complete reaction, and the reaction is very fast and reaches completion, we're going to boil the water first. So we ensure the water melts the maleic anhydride, which has a melting point of about 50 degrees Celsius, or 53 to 55 degrees Celsius. So we boil the water instead of just directly adding it, because it's usually better to heat the water first, then add your maleic anhydride so it goes into the solution, reacts, and forms maleic acid. So in this part, we're going to be introducing two new concepts: filtration. I don't think we covered that before. So we're going to use something called gravity filtration, and it's like this. So gravity filtration, we have our funnel. We're going to put a filter paper to collect the solid that may have formed in solution, and filter it so we can get only liquid at the bottom of the funnel. So you're going to put the filter paper here, filter your solution or your mixture, and you're going to discard the solid and just collect the liquid at the end. So in gravity filtration, you care about the filtrate or the liquid. You do not care. You usually do not care about the solid that you separated from the solution, if there's any. So we're going to use gravity filtration. Want filtrate, remove solid particulates. And why do we so this is a filter, but why do we want the filtrate while it's still hot? Does anyone have any ideas? Why do we want the filtrate while it's still hot? Any ideas? Okay, so we want the filtrate because if we wait till it cools, some maleic acid may crystallize out of solution. So we don't want that, because when we go to do this filtration, we're going to lose some maleic acid in this part, and it'll be contaminated with some other byproducts. So we don't want that. Okay, so remove any foreign material, and then prevent any maleic acid from crystallizing out of the solution. Okay. So the filtrate. So what's inside our filtrate? Well, if we look at our properties, maleic acid has some relative good solubility in water. So at high temperatures, most of the maleic acid will be in solution. So it'll be in our aqueous solution here. So our filtrate will contain the maleic acid. So what do we do with the filtrate? Do we throw it away or do we keep it? Someone hazard a guess. Do we keep it or do we leave it? Or let me ask you, is this the end of the experiment? Well, hopefully everyone says yes, or no. Yes, thank you. Keep it, right? We're going to keep it because we're not done with the experiment. So, so if people don't read the lab, they might think, oh, we're done, let's just leave. But no, that's not it. We're going to keep the filtrate and move on to the second part of the experiment. So we're going to let it cool to room temperature. For maleic acid to crash out a solution. And nope, we are not done. Okay. So once the maleic acid has crystallized out of solution, you're going to filtrate it through vacuum filtration. So this is the opposite of gravity filtration. You're going to keep the solid but usually the liquid, at the end of the day, you would get rid of it. But in this case, the liquid now is going to have your maleic acid in there still. So we need to keep it. So here's a sub here. We have, it's similar to this. The filtrate will contain most of your maleic acid. This Buchner funnel is what we use to collect the solid that crystallized from solution, connect this to a water trap and vacuum system. We connect it to a water trap because we don't want liquid to get into our vacuum line, because when it does, it will ruin it and we'll have to repair it. And that will prevent students from being unable to do experiments. So here's our vacuum or filter flask. It's also called Buchner flask because this guy developed these glassware for these types of manipulation experiment or like procedures to isolate products from reactions. So it's very some history here. Okay, so we wash the product with water. Why water? Because you don't want to wash it with like acid or anything because it'll probably react. Water is the safest thing. We want to use a little water and cold water. We don't want hot water because it'll dissolve the crystals again. And you want to be able to recover some of the maleic acid. So we're going to recover some of the maleic acid, and we're going to wash it with cold water to make sure that we're going to avoid dissolving the isolated product. So we use cold water, and we want to make sure there's no unreacted starting material. So, maleic anhydride, it'll react with water. So if there's any maleic anhydride on the solid, we want to remove it first before proceeding, because we want to make sure our product here is pure. So we're going to wash it with cold water so it doesn't dissolve the maleic acid, but it does react with the maleic anhydride in case there's some left over. Okay. What are we removing in the filtrate? So what's going to be in the filtrate? I think we covered that. It's going to be our maleic acid. So that's going to be carried on to the next experiment. So we don't have to actually redissolve our maleic acid here, and we can just carry on with the reaction further. Okay. Over this. So hopefully that was okay and clear. I guess I asked it too early, but no, we do not toss out the filtrate because we're going to keep it to use it for the next reaction. Okay. So part B, now we're going to convert maleic acid to fumaric acid. So I don't think anyone knows what reflux is. Maybe you've heard of it before in other chemistry classes, or maybe maybe by your own curiosity, but reflux is a way to generate heat to a reaction continuously over a long period of time. Yes, it's energy intensive. It wastes water. We're always trying to develop new reactions that don't use heat and does not need this setup because it's both environmentally unfriendly and it's wasteful. So that's why we're in the lab trying to develop greener ways to sustain, our society in general. But anyway, so we supply energy continuously to the reaction in the form of heat. So I'll explain how it works. When we do this, we allow reactions to occur much faster because remember, reactions have high activation barriers. Without heat, we can't get them to go. And this reaction is one of those situations, when you react alkene with acid, you're generating a very reactive carbocation. So as you might imagine, that requires energy to reach that activated intermediate. So it's very high in energy. So we need heat to get the reaction to go. Okay. So in a general sense, you have your stirrer hot plate that provides the heat to the system. In the lab, you're going to use something called a heating mantle, which is directly connected to a variac, which is a transformer, which you can moderate the amount of energy that you give to the heating mantle, which heats up the solution The solution will cause the vapor of the solvent to rise. And you see here, this is called a condenser. That's how we prevent the solvent from evaporating out of our system. So once the vapors reach the liquid here, the vapors reach the water condenser. So you see this condenser, it has a larger outer tube and a smaller, thinner inner tube. The inner tube is connected to the flask. This outer tube is closed off and is only connected up to this part. And once we put cold water through these lines, this will be where the water source is. It'll be cold, and this will be where we drain out the water. So you see here, to do this reaction for a long period of time, we are going to waste a lot of water. So the thing we do is, once it heats up, it reaches this where the water is, it'll condense back down to the liquid, and it'll fall back down and drip back down to the solution. So the level of solvent should always be the same. If your solvent evaporates and your solvent level goes down, that means there's a leak in your system, and so then you probably have to start over in that case. But this is how reflux works. We generate heat, solvent will evaporate, then it'll drip back down, and see that cycle will continue, providing a continuous source of heat to the system, allowing a reaction to occur. So this is how most organic reactions are done in reflux. Okay. So I explained the tubing right here with cold water, and I just the cycle will repeat, so no solvent is lost. All right. So there's not much you have to kind of know about reflux. You're just going to watch the video and see how it's done. But this is generally how it works. And this is a clamp. You would clamp this to like a stand or something so it's stable. Okay. And usually in this solution, you'll add a stir bar to maintain stirring, because I think you add boiling chips in the experiment. So you need boiling chips or a stirrer to maintain very smooth evaporation or reflux conditions. Okay. All right. So after that, we're going to be working up and analyzing the product. So we're going to isolate by filtration again. So which part is the waste? Do we keep or draw out the filtrate? So when we're isolating our product, it'll be a solid, right? So we want to keep the solid, but we want to draw away the filtrate because it contains maybe impurities, the solvent, and we don't want that no more. So we're going to discard it into the waste where it'll get treated and dealt with. Okay, because you can't send these things down the drain. These things need to be treated by waste management companies and people. Okay, so filter contains the waste that we don't want, so we throw that away. We're going to collect, dry, and weigh both products. So how we dry it is usually you run the vacuum for like 10 minutes, 5 to 10 minutes. And then you could dry it on filter paper, but usually it won't be enough. So usually in an ideal world, we would let it dry for over a week in your lockers, but we typically don't do that because we don't have time. Okay, so we're going to analyze our products by melting point. So the good thing about solids, you can analyze them by melting point, and usually if you compare them to literature values, it'll tell you the purity. So if it has a short range melting point, it's usually pretty pure. And when you have impurities, you're going to kind of broaden the melting point, and it usually lowers the melting point too, or it usually lowers or raises it based on what impurity there is in the mixture. But usually it makes the melting point very broad. So like say 101 to like 120, very broad, not sharp like 101 to 103. So it'll be very broad. So you're going to learn how we first prepare a sample for melting point, and then you're going to see how the apparatus we use to monitor and record the melting point. So in chemistry, things have gone more technically advanced. So we have very nice instruments now to record our melting point, and it actually records the melting point automatically for you, so you don't have to stand there and kind of watch it melt. But you should monitor it when you're doing these things in the lab. Okay, so the pure So the pure melting point for maleic acid is about 115. Fumaric acid is 299. So you're going to actually, there's a question in the post-lab that asks you why one melting point is lower and one is higher. So you should think about the structures of these two acids and think about the intermolecular forces between them and why would that cause one melting point to be higher than the other? Okay. Are there any questions about the lab? Okay. All right, so let's pay attention to this slide really now. So this is the data I need you guys to copy down because this is what you're going to use for the lab. So don't use the values in the video. If you do, I will have to mark you down. So don't do that. So use these values to complete the post-lab worksheet for the data collection. So here it is, part A. You're going to use this mass of maleic anhydride, use this to find the moles, and use it to find the theoretical yield of fumaric acid. You're going to find the mass of the maleic acid using these two values, and mass of fumaric acid that we collected using these two values. So with this information, you want to calculate the following: amount of maleic anhydride used right here, amount of maleic acid collected right here, amount of maleic acid in solution. So I'm going to give you a hint. Think about how much fumaric acid formed right here. Theoretical yield of fumaric acid. So you're going to use, so when you're calculating theoretical yield, you have to start from the beginning because we made maleic acid from maleic anhydride. And since maleic acid was used to form fumaric acid, you need to take into account the initial mass of maleic anhydride that you used. So that is going to help you calculate the theoretical yield for fumaric acid. Okay. Actual yield of fumaric acid right here, because that's the yield you wrote down, or the mass you wrote down for the isolated fumaric acid. So the stuff you weighed out at the end in the lab. But it's in the video, they'll have a value for you, but don't use that. Don't use those values. Use these values instead. Okay. Then lastly, percent yield of fumaric acid. Remember, fumaric acid, the yield will be the actual yield. So whatever this value is, divided by the theoretical yield. So the calculated theoretical yield from using maleic anhydride, converting that to mass of fumaric acid. So the theoretical yield is it's the yield that we should get if nothing goes wrong in the experiment. Like you have perfect reaction completion, perfect isolation technique, but you know that's impossible because you can't recover everything from the flask. There's going to be stuff that sticks to the flask, stuff that's lost during transfer. For example, when we transferred the filtrate from part A into another flask and let that cool. So there's always going to be some loss. And remember, some maleic acid crystallized, so that contributes to a loss in theoretical yield. So theoretical yield will never be 100. There can be 100. There's certain situations where there will be 100%. That's called quantitative yield. That means everything was converted. Usually in organic chemistry, you're like 99.99%. You just say a quantitative conversion, which is 100%. But here, we don't ever reach those numbers. And if you get over 100, that means your product is wet or has some solvent still stuck to it, or just not all the solvent has evaporated away from the solid. So for percent yield, there's going to be some actual questions in the post lab too, using as examples to practice calculating theoretical yield, I think actual percent yield. But so if you're having trouble doing it here, you're going to have trouble doing it in the post lab questions too. So come see me for help if you need have any questions about how to calculate theoretical yield for any chemical reaction or this reaction and so forth. Okay, so everyone, that is it for this experiment.